Hello everyone, welcome back to our channel and in today's video we are going to solve question on functions and recursions. I will be explaining the problems, build intuition using test cases, then solve it in these three stages. First, I will be discuss brute force, then I will be discuss better, and then I will be discuss optimal approach. And for every single approach, we will calculate its time complexity and space complexity properly. So by the end of video, you won't just know code that works. You will understand why it works and how good it is. So before we start, let's discuss and revise the concept of functions and recursions. So what is function? A function is a reusable block of code that takes some input parameters, performs some computation and optionally returns an output. Functions help us avoid repeating code and they let us break a big problem into smaller testable pieces. So now we think what is recursion? And recursion is when a function calls itself to solve a smaller subproblem of the same type until it reaches a case simple enough to answer directly. This is called the base case. The part where the function calls itself is called the recursive case. And every recursive function must have these two things. The first thing is a base case. Otherwise, the function will call itself forever and cause a recursion error. Maximum recursion depth exceeded in Python. Recursion limit in Python is, I think, around 1000. And recursion case that moves towards the best case, meaning the input must shrink or change in a way that eventually reaches the best case. Now, I will discuss how does the recursion actually work internally. The call stack. Every time when we call a function itself, Python pushes a new stack frame onto the call stack, which stores that calls as a local variables and where to return. When the base case hits, the stack starts popping. Each call return its value back to the call that invoked it. This is why recursion has memory cost. So every pending call sits on the stack until it resolves. So now I will be discussing that how can we calculate our time complexity of a recursive function. There are two common methods. Firstly, we will draw a recursive tree method. Draw the tree of a function calls and count how many nodes and calls exist and how much work is done per node multiplied. And the recursion relation, right? T of n in terms of T of n minus 1, n by 2, etc. and just solve it. For example, that T of n is equals to T of n minus 1 plus big O of 1 solves to big O of n. And similarly, T of n is equals to 2 times of T of n by 2 plus big O of 1 solves to big O of n. And now, how to calculate the space complexity of a recursive function? The space complexity is basically that our code, how much space it is taking. And in the space complexity of a recursion is equals to maximum depth of a recursive call stack at any point in time because that's the maximum memory use simultaneously. This is the different from iterative code, which usually use bigger of one auxiliary space unless you use extra data structures. And now I will tell you what is the difference between the brute force, better versus optimal, and why we were comparing these approaches in an interview and in real engineering work. The first solution you think is a brute force solution, and we deliberately solve every problem in three stages. Firstly, a brute force solution. Then we will be think about a better solution. Then we will think about the optimal solution where the time complexity is minimum and space complexity is minimum. So you build a skill of improving a solution. This is the single most important skill for coding interviews and for writing efficient production code. So this is all about our theory. So let's get into our questions. So the first question we will be doing is factorial of a number. Like, the factorial of a number, like I have given a number n, then you have to find n factorial. Like, I will show you. Yeah. So if I ask you, what is the value of 5 factorial? So it would be 5 factorial is equals to like 5 into 5 minus 1, 4, then again minus 1, which is 3, then again minus 1, which is 2, and again minus 1, 1, till it don't get to 0. Then compute its value, and its value is equals to 120. So this is known as factorial. So now we're building a intuition with the test cases. Like, what is the factorial of 0? Remember, the factorial of 0 is always 1. And we will do like we will make our this case as a base case. Whenever our value got 0, then we will return 1 because our value of factorial of 0 is 1 and factorial of 1 is 1, and I as I show you factorial of 5 is 120. So as factorial of 4 is 24. Like 4 multiply by 3 multiply by 2 multiply by 1. Okay. So notice something. Factorial 5 depends on factorial 4, and which depends on factorial 3, and so on down to factorial 0, which is our base case. So this problem depends on a smaller version of itself. So this pattern is exactly when recursion is a natural tool. So let's firstly we will do a brute force solution related to it, like a iterative loop. We will be do like defining, and we will be doing the iterative loop. this is our main formula. Result multiplies equals to I. And then simply I would return my result and I will do it like I am calling my function. So now let's run this. Yeah, see, our factorial of 5 is 120. So if I want for 6, see, 720. And if I want for like 10, see, 362,880. So let's compute its time complexity and space complexity. So see, as only a single loop runs, so its time complexity is bigger of n, the loop runs n times, and its space complexity is bigger of 1. Only a single variable result is used, no extra memory grows with the n. So this works fine, but it does not teach us recursion. And for many real problems, an iterative brute force isn't even obvious. So let's build the recursive version. So now we will doing a better version, which is our recursive one. So we will be doing, and if our n is equals to 0 or n is equals to 1, then I would return 1. So this thing is my base case. It is very much important. This is my base case. And I will return n into factorial of n minus 1. This is our recursive case. So now going to print it. Factorial of 5. Yeah. Now let's print this. Yeah, see, factorial is 120. So now I'm just dry run this recursive that how this comes. So see, when I call my function, which is factorial of 5, see what happens. Then this is passed as a n, then my n is not equals to 0 and it is not equals to 1. Then it will return n into factorial of n minus 1, means 5 into again factorial of 4. Then again my 4 is passed. Then again the base case won't hit. Then again it will return 4 into factorial of 3 n minus 1. So again it calls the function Now same, my 3 is not equals to 0 or 1, so it will return 3 into factorial of 2, 3 into factorial of, then again it will call for 2, and now it will call for 2 into factorial of 1. So now when it calls for 1, then it will see that my if n is equals to 0 or n is equal to yes. Now the base case hits. My 1 is equals 1, then it will return 1. Now this thing will be replaced by 1. And now this thing will be replaced by 2 into 1, which is going to be 2. And now call of factorial of 3 is replaced by my multiplication of 3 into 2, which is going to be 6. Now my call for factorial of 4, and again it is called for 24. And now this call, my main call, which is factorial of 5. Now it will give me the value of 5 into 24, which sums equal to 120. So see how the recursion works, and it gives my answer 120, like you can see here. So the time complexity is big of n. Exactly, the n recursive calls are made, and each doing big of one work, and which gonna be total big of n. And what about space complexity? And space complexity at the is big of n. At the deepest point, n stack frames exist simultaneously. Factorial 5 waiting for factorial 4, then factorial 4 waiting for factorial 3, then down to factorial of 1. So compare this to the iterative version. Same time complexity, big of 1, but recursive cost us big of an extra space because of the call stack, while the iterative loop only costs big of 1 space. This is a very important trade-off to always mention in interview. So now we will go towards our optimal solution, which is tail recursive style. As iterative is already optimal here, so for the factorial specifically, the truly optimal solution is the iterative one. As you can see, big of n time and big of one space version. We wrote first recursion doesn't give us any asymptotic improvement here, but Python doesn't optimize the tail calls anyway. So the optimal solution is this one, because it is taking same bigger of n time complexity, but space complexity bigger of 1. So even a tail recursive looking version still uses bigger of 1 stacks in Python. This is a good lesson that recursion is not automatically a better. Sometimes it's purely for code clarity. It is only for the code clarity. You understand? And here the iterative version is strictly optimal. So this is the core logic behind this question. So now let's move towards our another problem, which is nth Fibonacci number. So here the problem statement is find the nth Fibonacci number, where see, so I have to find the nth Fibonacci number, where f of 0 is 0, f of 1 is 1, And so we can we say that f of n is equals to f of n minus 1 plus f of n minus 2? Yes, we can say that. Firstly, what is Fibonacci series? I will show you 0, 1, 1, 2, 3, 5, and 8. So let's trace f of 5 manually first before writing any code so that the recursive structure is crystal clear. F of 5 is equals to f of 4 plus f of 3, first, second, third, fourth, fifth, which is equals to f of 4 and f of 3, and f of 4 is equals to f of 3 plus f of 2. Notice the f of 3 is needed by both the f of 5 and f of 4. This repeated need is the key insight for this whole question. Now we will move towards our first approach, which is, and now we will print this, and now we will run this. Yeah, see, it gives me the answer 55, and I want for 8, 21, and for 6. I got 8. So into Fibonacci 4 and Fibonacci 3, Fibonacci 4 branches into Fibonacci 3 and Fibonacci 2, and point out that Fibonacci 3 is computed multiple times. Fibonacci 2 even more times. This is overlapping subproblem. The exact signal that tell us that recursive brute force can be optimized. So the time complexity is big of 2 raised to power n, where each call branches into 2 more calls, forming a roughly binary tree of height n. And its space complexity is big of n, even though there are exponentially many calls in total, only one part down the tree exists in the stack at any given time. So max depth is n. So this brute force is correct, but terrible for such a large n. For example, I have to calculate for a Fibonacci of 40, and it would take several seconds because of 2 raised to power 40 calls. We need to remove the repeated work. So let's move towards our better approach, which is recursion plus memoization plus top-down DP. So If n in memo, then I would return MEMON, and if n is less than equals to 1, then I would return n memo, call for n minus 1, and then I will call for n minus 2, and then simply I would return my answer. So I will compute this for a very large value. So for example, I want to compute for 50. Yeah, see, I got my answer. So if I want to try for 40, 70, so yeah, we are catching every result we compute in a dictionary. The moment we need Fibonacci 3 again, instead of recomputing the whole subtree, we just look it up in big of 1. This is called the memoization, remembering results. And the time complexity is big of n, that each unique value from 0 to n is computed exactly once now. All the repeat calls are big of 1 lookups. And space complexity, it is big of n for the memo dictionary plus big of n for the recursive stack depth. So overall we can say it is big of n overall. So it is a better approach. So can you think about an optimal approach? Yeah, there is an optimal approach behind it. The bottom up iterative TP. Let's do the optimal approach. It is better. Yeah, same. So we will change its name to optimal. This is our base case where n where is less than equals to 1. Like it is equals to 1 or 0, then it will return that value. Then we will do for 2 and n plus 1. And then we will do our current value should be equals to my previous one plus previous two. And I would update my value. I would do that previous two value should be equals to previous one and previous one value should be equals to current. Like this is my core logic in this optimal approach. It should be equal to previous one and plus previous two. So this is the core logic in this question. So then I would return my previous one. Now I'm going to print. Firstly, I want for 5. So let's run this. Mm, yeah, see, answer 5. And I want for 10, 55. And now I want for a large value. Yeah, see. So here is the real optimization insight. To compute f of n, we never actually need to remember all the previous Fibonacci numbers, only the last two. So instead of storing a whole array or dictionary, we just keep two variables and slide them forward. So this improves the recursion entirely, avoiding the call stack overhead altogether. In our better approach, its time complexity is big of n, but the main concern is space complexity, which is big of n. So here we can see the time complexity is same, which is big of n, a single loop which is running from 2 to n. And here this we say our space complexity, which is going to be big of 1. Only two variables used, regardless of how large n is. So that is our optimal solution. So our brute force take bigger of 2 raised to power n and space complexity bigger of n. And our better take time complexity n and space complexity n. And this the most optimal solution. This takes same time complexity, but the major difference it creates in its space complexity, which is bigger of 1. So yeah, that is our second problem. So now we will move to our another problem, which is power of a number x raised to power n. So the problem statement states that compute x raised to the power n, and the test cases for the intuition to build is this. Like we call the function, passing my values. So it should return 102. and my another test case, like any other 3 raised to power 0, it would return 1, and this 5 comma 3, it would return 125. So, yeah. So what should be our intuition and what should be our approach for this? So let's think about a brute force where we can do the multiplications and then we will check our test case. It is brute one, and making my variable which values equals to 1. And simply I would return my result. And then I would print it. Then I would check my first test case. Yeah, see, 1024. I want to share one thing that if I would do my value result is equals to 0, then think what happened. Yeah, it will always going to return a value 0. Why? Because in this logic, it would multiply by number every time with 0. So multiply a number 0, always give a 0. So keeping it 1 is very much important. And we will check our another test case. 1, and another test case 125. So this takes our time complexity of bigger of n and space complexity bigger of 1. So let's try to solve this question using recursion and see whether it would be a good approach or not. Let's firstly do the question using recursion, and this is my base case that if n is equals to 0, then definitely I would return 1. Turn x into power recursion, comma n minus 1. Now let's check it. Firstly, give my first test case to it. Yeah, see, 1024. And if, for example, I would return value 0 and see what happened. Yeah, 0. Similarly, like this question, it will return value 0 and 0 multiplied with any number is equals to 0. That keeping it return 1 is very much important here. I was testing my another test case. See, value 1 and 5 comma 3. Yeah, see, 125. So now let's discuss about it time complexity and space complexity. So same as brute force, just write it recursively. So it takes big of n time complexity, but what about its space? Space complexity it takes is big of n, a recursive stack depth n, which is actually a worse than the loop version in terms of the space for the same time complexity. Point this out that recursion isn't automatically better. Here it is strictly the worse than the loop, since it has the same but extra space. So now we will be doing the optimal solution for this. And here is the real insight behind this optimal approach, which is having the fast power divide and conquer approach. And the real insight is basically if we do x raised to power 10, that it would be equal to x raised to power 5, then whole power 2. Like I will explain you like if I do x raised to the power 10, tell me, is it equals to x raised to the power 5 and whole raised to the power 2? So yeah, it's equal. X raised to the power 10 is equals to x raised to the power 5 raised to the power 2. So if n is even, we can compute power x comma n by 2 once and just square it instead of doing n multiplication. This is known as the fast exponentiation or binary exponentiation, and it is used everywhere from cryptography, RSA to competitive programming. So it is very much important. So let's do it. And same our base case. If n is equals to 0, then I would definitely return 1. Then I would call my function and I will do and if my n is divisible by 2 and divisible by 2 it means that it is an even number, so I would return half into half, and else I would return x into half into half, then printing by calling my function for calling my first test case. Yeah, see, 1024, 3 comma 0, yeah, 1, 5 comma 3. Yeah, see, 125. So let's do a dry run for my 2 comma 10. Gives myself 1024. So see, when I call my function power 2 comma 10, then what should be its half? Its half would be its half will be 2 comma 5. Yeah, and its another half would be 2 comma 2, and squared and odd means x into half into half. So, and when the n is even, when n is even, and it would return half, and it would return half into half. So this is a dry run of my 2 comma 10 code. So that's give me 1024. So think what should be its time complexity? Actually, its time complexity is bigger of log n. Every recursive call half the n. See, when I call 2 comma 10, half to 2 comma 5, half to 2 comma 2. So exactly like a binary search, like t comma n is equals to t comma n by 2 plus big of 1, which solves to big of log n. See, and its space complexity is big of log n. The recursive stack depth is log n now, not n. So here its time complexity is log n, and space complexity is log n, and in there my time complexity is n, and my space complexity is big of 1, and in my recursive solution my time complexity is big of n, and space complexity is big of n, the recursive stack space. So our next problem is GCD of two numbers. So, but if the problem statement says that find the greatest common divisors of two numbers A and B. So our test case would be 48, comma 18, 17 comma 5, which is equals to 1, and it's gonna be equals to 6, 25 equals to. So my approach for this question, can I use a subtraction based recursion on this? Yeah, I can use. I can do a recursion call, and I can create a base case that if I found a value where A is equals to B, then it would return A, and if A is greater than B, then it would return uh, something like A minus B, else B minus A. So let's do this. Like if it is equal, I would return either A or B. And if my A is going to be greater than B, then I would return by calling my function, like I would call like A minus B comma B, or else I will return I will return A comma B minus A. And so this is the core logic behind it. If my value of A is greater than B, then I would do A minus B comma B, and else it means that my value of B is greater than A. Then I would do B minus A. And now just printing my answer, call like, yeah, I will call like 48 comma 18. Let's run this. Yeah, 6. And testing our other test case. Yeah, see, 1, 100 comma 25. Yeah, see, 25. So this is that checking every devices. But if the number are very different in size, like I would say I want a GCD of like 10,000, 10 lakh, comma 1, would it subtract a 10 lakh or 10,000 times? That is very much slow in the worst case. So think that what should be its time complexity? And and you know that we calculate the time complexity in the worst case. So its time complexity would be maximum of A comma B. Yeah. It should be the maximum value of A comma B. And think about space complexity. We are doing a deep recursion in the most case, so definitely it would be by max of a comma b. Yeah. So this is my one of the approaches. So let's think about another approach where we will check every divisor. Yeah, we will do it like, and result is equals to 1. And if we will do is equals to 0, then it then this code not uh, run, and gives us the wrong output. Like if I will do it like 0, then it would return GCD if in the case of 17 comma 50. But I want 1, so I will initialize this value as 1. We'll do minimum of a comma b. Definitely 1. And I will put a if condition like if my a modulo I is equals to 0 and b modulo I is equals to 0, then my result would be equals to I, and then in the end I would return my result. Yeah, so let's call my function like 48 comma pp. Let's see. Yeah, 6, and another test case. Yeah, C 1, and another test case of it comma 25. Yeah, C 25. So think about its time complexity. So its time complexity would be minimum of a comma p. We loop through every numbers up to the smallest value between a and b. And what is about the space complexity? Cause it is big of 1. We are not using any extra space. So this solution is better than this solution. This solution having time complexity of maximum of a comma b. And this approach is having minimum of a comma b. And space complexity is 1. So it is far better than this approach because we save our space too. And so can we think about a more better approach than these approaches where we have a time complexity and space complexity better than that? Because yes, there is an optimal approach which is known as Euclidean algorithm using modulo. So when writing the code, sorry, optimal, and if b is equals to 0, then I would return a, and this would return optimal of b comma a modulo b. Then I would call my function GSP optimal, and I would test with my first test case 48, 18. Let's run this. See, 6, and another test case like 1. Yeah, 25. And now I would test for a very large number, comma 7. Yeah. So instead of repeated the subtraction, we jump straight to the remainder using the modulo operator. This modulo operator. So this is a Euclidean algorithm which is known since the ancient Greece, and it is probably one of the fastest way to compute GCD. Fun fact is, as the worst case for this algorithm, the slowest possible convergence happens on consecutive Fibonacci numbers. So the time complexity and what should be its space complexity. Let's think. We are doing this modulo operator. So its time complexity would be log of min of a comma b. So it is better than my previous approaches. The number shrinks roughly by a factor related to the golden ratio of each step given logarithmic time, and my space complexity would be recursion depth matches the time complexity here. It would be log of min of a comma b. So, yeah. So see, my first approach gives me the time complexity and space complexity of max of a comma b, and my second approach gives me time complexity of min of a comma b and space complexity of b of 1, which is better than this approach. And my optimal approach, it gives me the time complexity of log of min of a comma b, which is better than these approaches. Okay, so this is our question of finding GCD between two numbers. So now let's move towards our another problem, which is subset sum problem. So firstly, I would make it so in this question, they given an array of numbers and a target sum. Determine if any subset of the array adds up exactly to the target, and the test case intuition is basically that this is an array. The it is true. Why? Because here this 4 and 5 gives me the sum 9, and my another test case, and target 7. So it is false because max possible combos don't reach 7 cleanly. Let's verify because it don't make any sense because 1 plus 2 plus 3 won't give me 7. It give me 6. So this is a false. Yeah. So for every number we have exactly two choices. Like if I want to include it into my subset or not. That include or exclude pattern is the classical recursion signature for these problems. So, what should be my brute force approach for this? That it should be that try every subset via recursion. So, it would be this approach would be like brute force, and I would pass here index 0. And if my target is equals to 0, then I would return true. And if my index is equals to length of nums, or my target is less than 0, then I would return false. Then I would include, and I will do index plus 1, and in exclude, and I would do like nums target and index plus one, and I would return either include or exclude. So now let's run this by calling the function. I'm passing my first test case, yeah. Now let's run this. Target. Oh, sorry. I have to do it like, yeah, yeah, like, yeah. It returns true. And let's check for our another test case. This one, and passing my value 7. It should give me answer. Yeah, false. So let's think about its time complexity and space complexity. Hmm. So every element has two choices, either to include or exclude. So it would be giving 2 raised to power n total leaf calls in the worst case. So its time complexity is equals to 2 raised to power n. And for its space complexity, it is big of n, as max recursion depth equals to the number of elements. Yeah. So it is time complex and space complexity. So let's think about a better approach for this. I think it would be recursion and memoization. Yeah, it should be. So we are making our function. Yeah, and if my memo is none. Yeah, memo is equals to, and my key is equals to index, comma, target, and if my key in memo, then I would return memo of key. And if my target is equals to 0, then I would return true. And if my index is equals to length of nums, or my target is less than 0, then I would definitely return a false. If my index is equals to my length of my array, or target is less than 0, then I would return false. Yeah. And I will do include nums of target minus index, comma, index plus 1, comma, yeah. And I will do exclude equals to my nums, comma, and index plus 1 memo, and I will do that memo of key. Oh, yes, it is equals to include or exclude. Then I would return my memo of key. Now just calling my function. Yeah, yeah. 4, 12, 5, comma 2. You will be sending 9. Subset sum, comma target, It is returning true. Then I am calling my another test case 1, comma 2, comma 3, and yes, yeah, it is returning false. So the overlapping subproblem here is the pair index, comma remaining target minus the same index target state can be reached through different inclusion and exclusion paths. So we catch on that pair and think that what should be its time complexity and space complexity. Yeah, its time and space complexity is n into target, as there are at most n into target unique index comma target states, each computed once. So its time complexity would be n into target, space complexity would be n into target. So space complexity like that for the memo table plus ON recursion stack. So this would be our better approach. And let's think about that. What should be the optimal approach? It should be a bottom-up tabulation DP. Yeah, it is solved using the dynamic programming. So we will do like where my n is equals to length of nums and my dp is equals to falls into target of plus 1, mm, we do into brackets, and it should be in range n plus 1, 1 comma n plus 1. So no, it should be n plus 1. Yeah, and we will be do like, so it would be like sum is equal to 0 is always achievable. Empty subset. So and now we will do for I in range like for t in range 1 comma target plus 1, and if my nums of I minus 1 is less than equals to t, then my dp of I of t, it would be dp of I minus 1 t minus nums of I minus 1, or dp of I minus 1 t. Yeah. And else it would be I t equals to, yeah, then I am returning my dp of n and target. Yeah. So I would calling my function, yeah, and my test case 334 4 12 5 2, passing value 9. Let's see. Yeah, returning true. And now I am passing my second test case 1 2 3 and 7. Let's run this. False. So here we build the answer bottom up using a 2D table instead of a recursion. So there is a zero call stack overhead. This is the standard way a subset sum is solved in production and in interviews where when n and target are both reasonably small and its time complexity is big of n into target minus filling an n plus 1 into target plus 1 table and big of 1 per work per place. So its time complexity would be n into target, like filling an n plus 1 cross target plus 1, and its space complexity would be big of n into target for the table, and this can be optimized further to big of target using a rolling 1D array, and this should be a bonus optimization for this question. So in this question, our brute force solution, which is recursive one, using the time complexity of 2 raised to power n and space complexity of n. And in our better solution, that memoization solution, the time complexity is n into target and our space complexity is n into target, which is better than this approach. And in our optimal one, the tabulation one, time complexity is n into target and my space complexity is n into target. And remember, this space can be optimized to only target. Okay, so our next problem is printing all the permutations of a string. Let's assume that we are given a string and we have to print all the possible permutations, rearrangements of its characters. Like, like if example I have a test case like A B C, then it would be A B C, A C B, B A C, B C A, C A B, and C P A. Means three numbers, three factorial. It means 1, 2, 3, 4, 5, 6. Okay. So there is no meaningful brute force versus optimal here in the terms of complexity. Generating all the permutation is infinitely big of n factorial. No matter how you do it, because there are n factorial permutations to output. But there is a less clean versus cleaner, more efficient way to build them. So let's compare both the approaches. So my first approach, so my first approach is about that building new strings by slicing at every call. Like I will mark as a first approach if length of my s is equals to 0, then print my path and return. Yeah. And for I in range length of s, permutation first, s of I plus s of I plus 1 path of plus s of I. Yeah. So I am calling my function and here I am passing, yeah, ABC, ACB, BAC, BCA, CAB, and CBA. 1, 2, 3, 4, 5, 6. Yeah, 6. And if I would do like I have to A, B, C, D input, then yeah, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, exactly 21, 24 outputs means 4 factorial, 4 characters, 4 factorial, so 24 outputs. So think that what should be its time complexity and space complexity? Its complexity would be n factorial into n. N factorial into n. Well, n factorial permutations, and at each of the n levels of recursions, we do big O of n work for a string, slicing, concatenation. Strings are immutable in Python, so every slice concat creates a new string. So, what do you think about space complexity? Yeah, it is same. It is n factorial into n. If you count the space for all the printed outputs, but auxiliary space ignoring the output is big O of n for the recursion depth plus big O of n per call for slicing. It is equals to effectively big O of n square auxiliary in the worst case. Why? Due to the string copies. So the second approach, I think I can think about in place swapping using a list. So, so the second approach would be like I would name it as second, and if that L is equals to, so we will be doing that printing dot join characters. Yeah, and I would return and for I in range L comma length of characters, I would be do like do like char of I comma character of L. Sorry, it is yeah, and yeah, permission second comma L plus one should be equal to mm, I plus of L. Yeah. So I would do like this, passing the list A, B, C. Yeah. So now let's run this. C. 1, 2, 3, 4. Yeah. All the permutations are printed. And if I would like to do for A, B, C, D, yeah, see, all the 24 are printed. And if I want for AB, yeah, only 2. 2 factorial 2. And if I would pass yeah, A. So instead of creating a brand new strings at every recursive call, can we swap characters in place inside a list, recurse, and then swap back? This swap, recurse, and unswap pattern is the essence of the backtracking. This avoids the overhead of the repeatedly copying the strings, which we were doing in this one, and what should be its time complexity? Yeah, it should be big of n factorial and n. Yeah, and yeah, and it should be its space complexity. It should be big of n auxiliary. Yeah, because only the recursive stack, since we are mutating one shared list in place instead of creating a new string at every level. So yes. So now let's compare the time complexity and the space complexity in both. In the brute force, where we will do string slicing in this, here the time complexity is n factorial into n and space complexity is n square due to the repeated string copies. So this is the problem with it. So a optimal solution for this could be this solution where time complexity is same. It is big of n factorial into n, but we save our space in the space complexity, which is big of n. So that is all about this question. So now we will move towards another very important question, which is tower of Hanoi. So this is very important question. Yeah. So in this question, its problem statement is that move n disks from a source rod to a target rod using an auxiliary rod such that a larger disk is never placed on a smaller one, moving only one disk at a time. So this is the problem statement of Tower of Hanoi question. So this is a pure recursion theory question. There is no meaningful like the brute force versus the optimal one because the problem is of the minimum number of moves is mathematically proven to be 2 raised to power n minus 1. So instead of comparing approaches, let's use this right, question to deeply understand that how to derive a reoccurrence relation from scratch. Since that skill applies to every recursive problem. So, what should be the recursive idea? So, it would be an that to move n disks from source to a target using auxiliary. So, moving the top means that n minus 1 disks from source to auxiliary using a target as a helper and moves the biggest disk directly from source to the target and move the n minus 1 disks from auxiliary to target using source as a helper. So this gives us the reoccurrence. The reoccurrence that like this would be equal to 2 into n minus 1 plus 1 and with t of 1 is equals to 1 means that one move for a single disks. So this is all the recursive idea behind this question. So let's implement this recursive idea into our code. So it code would be like comma target. Yeah. So if my n is equals to 1, then I would do printing my f string and move disk 1 from my source to my target. So I would return this. So now I'm calling my function again recursively, where I call like n minus 1, comma source, comma target, auxiliary. Yeah. And then I am printing, and here I will use my f string, move disk n from source to target. This is would be my step 2. Yeah. And my step 3 would be again calling my function which is n minus 1, comma, auxiliary, comma, source and target. Source and target. And now I am calling my function tower of 108, comma, A, B, well, yeah, C. Yeah, C. Move disk 1 from A to C, move disk 2 from A to B, move disk 1 from A. So, yeah. So, what should be its time complexity and space complexity? So, its time complexity would be 2 raised to power n, proven both by the recurrence solving and intuitively. And since the number of function calls doubles at every level of n, when you will be do it like in a like you will when you will be do a dry run by own using reoccurrence, then you will find its time complexity is big of 2 raised to power n. Yeah, and its space complexity is big of n. The recursive depth is exactly n, since each call reduce n by 1 until reaching the base case n is equals to 1. So its space complexity is 1. Yeah, yeah. So now finally we will be at our final question, which is a binary search. We will write a code for a binary search problem. Like, what is a binary search? We will write its algo. Like, we will given a sorted array and we will find the index of a target value. And I will tell you that its time complexity would be log n. It is the fastest way to search and find the index of a targeted value. So the so the intuition behind it is that our no that we already know that our array is sorted. So can we do it like in big of one space, and we will be do iteratively with the while loop, and uh, let's understand this all the things that how we can work this algo in big of log n time complexity and space complexity of big of one, which we will be doing iteratively with the while loop. So making my function binary search, where we are providing array and a target, and we will be doing and 0 array minus 1. and we will do like while my low is less than is equals to high, and we are finding the mid using a formula which is low plus high divided by 2. Covering it in brackets. Yeah, yeah. And see if my value is equals to target means I found my value and just I have to return the index of that value. Then I would return, and if my array of mid value is less than my target, then my low is at a lower number. Then I would increase it. Then I would be doing that low pointer. Please move towards mid plus one. Yeah. And in the else case, and in the else case that when my array of mid is greater than my target, then I will tell to my right pointer that move towards mid minus one, my high pointer, mid minus one. Yeah. And if I don't find any of that index, then I would definitely return minus one. And I'm making my array a sorted array. Remember, this is applicable only on a sorted array. Yeah, see, it is my sorted array. And now I am just calling my function and passing my values. I pass my array. And for example, here my target is like, for example, 8. Yeah, 3. 0, 0, 1, 2, 3. Yeah. So it return my index of my target value. And for example, if my target value is not there, for example, it is 7, then what happened? It returned minus 1 as this. So, so I will tell you why the sorted array is very much important. For example, this array is not sorted. For example, this array would be like this. like 21, comma 2, comma 4, comma minus 2, comma 54, comma 22, comma 8. Like this is unsorted array. Then it would return a it would return minus one, or it would return a wrong value because it don't applicable at unsorted array, because this my core logic is strictly applicable on a sorted array. Like earlier it was like 2 comma 4 comma 6 comma 8 comma 10. Here, like if you see that this value, like this value is less than my target, so it would say to the low that please move towards the mid plus one. And if it is opposite of that, then it would say to the high pointer that move towards mid minus one. So what is the time complexity? I tell you earlier that its time complexity is bigger of log n, and reoccurrence like t of n is equals to t of n by 2, like plus beta of 1, and solves to log n. Since the search space halves every call, yeah, so its TC is log n, and it is the fastest searching algorithm. So, what should be its space complexity? And is its space complexity is big of 1, because we are not using any extra space. We are just using uh, the iterative approach of while loop. And if we think about that, if we want to if we want to do this question using recursion, and we will definitely do, but then its space complexity would be log n. It would be a recursive stack space. Okay, so let's quickly recap everything we covered today. We didn't just write 8 pieces of code for every single question. We followed the same discipline, understand the problem with the test cases, we'll write the brute force and identify why it is slow and improve it step by step. And we will always calculate its time and space complexity honestly, including the hidden cost of the recursion call stack. And we compare the time complexity and the space complexity of brute force, the better solution, and the optimal solution. So here is a big takeaway theory point of recursion space complexity is not free. It's always at least the depth of the recursion tree, and that is something a lot of people forget when comparing the recursive versus iterative solution. Here you can see this iterative solution uses space complexity of big of 1, whereas if we do this same question using the recursion, it would take log n. So if this deep dive style helped you actually understand the recursion instead of just memorizing the patterns, let me know in the comment section. Like the video and subscribe to my channel for more deep dive content. See you in the next video.